So today, Julian, our vice president, is going to give a talk / discussion on a topic that he will introduce.
Okay, so I'm just gonna share my screen. All right, so my topic is about these math things called dessins. And what that, I'll get to what those are in a minute. So basically they're going to be like graphs that live on topological surfaces. So I'm just going to, so like the beginning part of this, I'm just going to like go through some definitions so that we know what these surfaces are. And then once we know what the surfaces are, then we can start talking about things that are on the surfaces. Okay, so first, as you can see here, I'm going to, all right, so topological surface. A topological surface is, well, there's kind of there's an intuitive notion, and then there's like a more precise definition. So first I'll talk about the intuitive idea, which is that a topological surface is a space that looks like C when you zoom in really close. So C is just the complex plane, so it's the set of all complex numbers. So a topological surface is just something that, like, maybe on a large scale it's shaped very differently, but like on a small scale it'll almost look like just the complex plane. And so a more precise definition is, don't worry if you don't fully understand the precise definition, because it's kind of a lot to take in, but I'm just going to go through it anyway, just for those of you who might be interested. So a space X is a topological surface if, first of all, X has to be Hausdorff, which is, again, like, I'm not going to get too much into what that means right now, because we're not really going to use this too much in this presentation. I'm just like putting the definition here to have it here. And then the second condition is that we can find a collection of open sets in X and homeomorphisms from these open sets to the complex plane, such that the union of all these open sets covers all of X, and if two of these open sets are disjoint, then the composition of these, like, of the one homeomorphism with the inverse of the other homeomorphism is also a homeomorphism. So like these, like this phi j of phi I inverse functions, these are called transition functions. So basically, condition B says that the transition functions have to be homeomorphisms. Okay, so essentially what this definition basically means what the intuitive idea is trying to say. Complex one manifold. I believe that is what, yes, I think that is what you could also say. Right, so yeah. But again, like, if you're having trouble understanding what this precise definition means, like, again, just like refer to the intuitive idea that this precise definition basically just means that it looks like the complex plane. So there are also some like special surfaces with like extra conditions and structures that we call Riemann surfaces. And those are really important for talking about dessins, which I'm going to get to in a minute, but we're not really going to be using the Riemann surface structure in today's discussion, so I'm not really going to define that right now. So, but just like as a side note, that is important for this topic too, if we like want to look into it at a later date. Okay, so I'll move on now. So let's think of some examples of surfaces. So does anyone in the audience want to like give an example of something that might be a surface?
The complex plane.
Yes, very good. The complex plane is one example of a surface. And so I didn't draw it before, but you know, the complex plane just looks like that, right? It's just plane that goes on forever in all directions. And if you're used to working with real numbers, it looks pretty much just like the real plane, so like R2, except instead of like using real number coordinates, we use complex numbers to refer to each point. Anyone else want to volunteer examples? Yes, that would be, right, so that's P1C, right? Yeah, so that would also be
That's just a sphere.
yeah, so right, so that is the sphere. So that's just for those of you who don't know what P1C is, it basically is a sphere. So the sphere is also another surface, and by sphere we basically just mean literally a sphere. And the other, yeah, Taurus. Taurus is another one. So yeah, there are more than 6 surfaces, by the way. You all just happen to be listing ones that I had listed on this grid. All right, so Taurus, for those of you who don't know, a Taurus is just kind of a donut shape. A Mobius strip, yeah, so the Mobius strip is a surface. But in our discussion, we only want to, I haven't said this yet, but we do want to focus only on orientable surfaces, and the Mobius strip is non-orientable. So yeah, so that is a surface, but not really one that we're going to talk about today.
A cylinder.
Yeah, so a cylinder is another surface, and actually a cylinder is actually going to wind up kind of being equivalent to the sphere, because if you think about it, like if you take this cylinder, like you can kind of like, if you like kind of puff out the edges and like expand it a little bit, you can kind of warp it into a sphere. So those are
Wait, no, I meant like an annulus.
Oh, right. Okay, yeah. So that is another surface. So yeah, so the cylinder Eben is talking about is the cylinder that like has nothing. It's like not including these circles on the edges. So it's just kind of the hollow shell. Right. So yeah, so okay, and I'm just gonna go over some more examples I have here. So we also have that the unit disk. So D is the unit disk. So it's basically everything like inside of a circle except for the boundary of the circle. We also have the upper half plane, which is basically everything on the complex plane that's above the like x-axis. So it's everything up here. And we also have, going along with the torus example, you could also take a torus with like 2 holes in it instead of 1. So that'll look something like this. Is basically, it's just a double donut. And you could also take a torus with 3 holes or a torus with 4 holes and so on, and those will all be surfaces. Okay, so moving on. Now we're going to define like the main character of the discussion, which is a dessins de font. So what the name literally means is, it means like, it's French for child's drawing. So they're called such because because basically they're like easy to draw, essentially. Like they're like really simple to look at, but they do still have some very interesting math going on. So what a dessine font is, and sometimes we'll shorten it just to dessine, because why would you say two words when you could just say one? A dessine is a pair x comma d, where x is an oriented compact topological surface, and d is a subset of x that is a finite graph. So before I move on with all the rest of the conditions of this notion, we'll just like kind of break down what this means. So compact basically means that we don't want our surface to go on forever or to have any like fuzzy edges. So of the examples we drew, that means that we're not like talking about like, we don't like, the complex plane is not compact because it goes on forever. The disk is not compact because it has like because it doesn't include this boundary. And the same with the upper half plane, whereas the sphere, the torus, and the two-hole torus, and like any other number of hole torus, those will all be compact. So these down here are more the surfaces, the types of surfaces we're going to be talking about. And right, and oops, hold on. Right, we also want our surface to be oriented. So again, no Mobius strips. So and for those of you who might not know what that means, it basically means that like you can pick like a consistent notion of like direction on your surface. We're not gonna delve too much into the details with what oriented means, but yeah, you can't have any, like what the Mobius strip is, which is the thing you can't have, is it's basically like, you know, if you take kind of this like a flat piece of paper and then you kind of like twist it around like that, right? It kind of looks like this, where it's, and like if you like kind of follow along the edge, this only has like one face, and it winds up being that like if you try to define a direction on this, you can like follow your finger around and wind up like getting at the same point but pointing in the opposite direction. So that means it's non-orientable, so you can't like, there's no like consistent directions on this. So we don't want any surfaces like that, because they're not as like nice to work with in this sense. So, all right, and finally, one last word I should talk about is graph. So what a graph is, there's like a couple meanings of graph, but right now, the type of graph we're talking about is, it's basically a set of vertices that are like connected by edges. And they can, you know, they can be connected however you want them to be, but yeah, so that's like what a graph is, just you put a bunch of points and connect them in some way, like connect the dots basically. So we have a surface and we have a graph on the surface. And the conditions that need to be met is, first of all, the graph D has to be connected. So what that means is that like you can't have like two separate islands floating around. They have to be connected together. So connected basically means exactly what it sounds like it means. D is bicolored. So now this is a little bit, so right, with the normal graph, you can just take like what bicolored means is that we're taking like two different colors of vertices. So like in this context, we'll just call, I know I'm writing in like purple here, but I'm still gonna call like the solid colored ones, I'll call black vertices, and like the open circle ones, I'll call white vertices. So basically, D being bicolored means it has to be made up of both black vertices and white vertices. And the rule is that you can't connect a black vertex to a black vertex, and you can't connect a white vertex to a white vertex. So the black vertices can only connect to the white ones, and the white ones can only connect to the black ones. Like you can't do this. So if you were trying to do this, you would have to put another vertex there, because otherwise it wouldn't work. And the same like over here. Okay. And then the third and final condition is that if you like take the surface, if you like take away all the points of the graph, what's left over is like the union of like finitely many topological disks. So what a topological disk is, it basically means that you can like bend or stretch it to look like the unit is. So it's basically just it's kind of like a face of a surface, or of, yeah. So okay. Does anyone have any questions so far? Because I might have gone through this a little fast. Right, yeah, so the graph does have to be embedded in a surface. So, you know, in this, when I like doodled this graph that I have over here, right, this one, whoops, this one here, I didn't really draw it in a surface, but like, they do have to be, you do have to imagine that these are located on some type of surface. And again, like the surface is like any compact oriented surface. So it could be like a sphere, or torus, two-hole torus, etc. So yeah, these graphs are, when we're talking about dessins, they're always going to be on one of these surfaces. Just by the very definition. Okay, any more questions? And if not, I'll move on. Okay, I'll move on now. So now, and the one important definition to keep in mind is that is the genus. The genus is going to be a very important feature of both the scenes and the surface of the scene. So we define the genus of the scene to be the same as the genus of X. And well, what's the genus of X? Well, for the surface, if we're going to be talking about, the genus is the number of holes. So again, like looking at our example compact oriented surfaces up here, the sphere has genus 0 because it doesn't have any holes in it. The torus has genus 1 because it has just this one hole. Two-hole torus has genus 2. A three-hole torus will have genus 3, and so on. Next, there is like a notion of the scenes being equivalent to each other. So again, there's like kind of a lot of words here. Don't worry too much about the exact words or definitions, but the intuitive idea is that basically if we have like two dessins, x1, d1, and x2, d2, we can take like a nice map from x1 to x2 that basically makes d1 look very similar to d2. So that like takes d1 to d2 like in a very nice way. So it's basically, so yeah, so it's a nice map that maps nicely between the graphs. So, and then also, and if you have like, you know, like I was saying before, you need to, in order for it to be for a graph to be like part of a descent, it has to be bicolored. And you might be like, but wait a minute, what if I have a graph that isn't bicolored and I really like this graph and I want to use it, right? So I don't know, here's just, you know, maybe this is your graph. well, you can turn it into a dessine just by placing more vertices on it. So you just have to place a white vertex between all these black vertices, and now you can say it's a dessine. All right. Any more questions before I move on?
Right. So when you said it says that two dessines are equivalent when there's an orientation preserving homeomorphism. Does that mean that you can, that on the surface of the given do x1 and x2 have to be the same topological surface?
Yes, because they have to be. Do you know what homeomorphic means?
I do not.
Okay, so basically a homeomorphism is it's a map from like one surface to another, where like you bend or stretch the original surface without cutting it and turn it into the new surface.
Right, got it.
And so yeah, so like and like when there exists a homeomorphism between two surfaces, we say they're homeomorphic. So like an example would be like, like if this is a torus, this is homeomorphic to, I don't know, you could have like some other thing here.
Like a straw?
Yes, but provided that the straw has like some thickness to it.
Right, yeah.
Yeah. Yeah, coffee cup is the famous example, is that you can turn a donut into a coffee cup by like, because the coffee cup has this hole here, and you just kind of like fill up this space and then just kind of like stretch it around a little, and you can turn it into, so basically, yeah, so like, and what you probably need to understand most like for today is that like any of the surfaces we discussed that have the same number of holes will be homeomorphic.
Got it. And if you have time for it, could you please define isomorphism? Sorry, I'm really sorry.
Okay, so yeah, so I don't think I could talk about that a little more at the end, because that will involve kind of a lot of other definitions before I really like say what that is. Yeah, so I'm going to move on for now. If we have time for that, I'll get back into it. But yeah,
Thank you.
yeah. So there's also some good comments people are making here. All right, so I'm gonna move on for now. So one kind of important point to emphasize is that dessins are not just abstract graphs. So an abstract graph would be like, if you took, can you see my cursor?
Yeah.
Okay. Yeah, for example, if you took this thing here and it was just floating in air, that would kind of be an abstract graph. But our dessins aren't just floating in the air. They are like on a particular surface. Okay, so for example, and the picture I'm about to show, I didn't draw myself. I got it from a book, which I will cite at the end of the discussion. So if you have this dessine here. So this dessine is a sphere and then this kind of tetrahedron shaped graph, right? So you can just look at the picture and see what that means. And then also here you have this other dessine, and this one's on a torus. And if you forget about the surfaces and just look at the graphs, like if you just imagine those two graphs floating in space, you can like kind of bend them around and turn them into the same graph. So like they're the same abstract graph, but they're not the same dessine because they're on different surfaces, right? So like, whoops. Right, so either one of those two graphs you can bend into this shape. But it doesn't matter that you can bend them into the same shape because, and we'll see in a minute that like that this kind of, there's a reason why this doesn't work because, yeah, so I'll explain that more in a minute. Or maybe, I don't know, I'm stuttering, so I'll next thing. Okay. So, right. That's just saying we'll see, so right, we'll see in a minute to like how we determine how we can tell these two dessines apart even though they're the same abstract graph.
Well, I have a question. Do they have to be connected?
Yes, they do.
Okay.
Yeah, that is part of the definition. Yeah, so
I'm sorry, I didn't see that.
yeah, that's condition 1. So yeah. And right, so all right, so for now I just want to kind of pause and like have some audience members come up with maybe examples of dessines. So like pick a surface and then draw a graph on it, I guess. You should be able to. Is annotation enabled? If so, then you could. Yeah. So annotation is enabled, so you can like draw on the screen if you want to.
Hey, Julian.
Yeah.
So like, if you have a genus N surface, and you like poke a hole in it, it pulls back to like a rose with two end petals. Could you like embed that back in and make that a dessine? Like for the two-hole torus, you'd have like 4 different little petals coming out of like a central node.
I'm not exactly sure what you mean by that. All right. Oh, someone asked like, all right, can you connect all the vertices of a cube? You can, but you would have to add. You would have. Yeah, but if it does, you could try it yourself and see if you're able to work it out in a bicolored way. Okay, yeah. So if you don't want to draw on the screen, like you can just like, like just draw for yourself on a piece of paper or a notebook or something, just like a graph. But yeah, with the cube, let's see. So we want to make this bicolored. So let's see if we can do that. All right. So so it looks like we can do this. So yeah, you can have it dessine like that. Okay. I'm going to. Does anyone else want to say anything before I move on?
Do they have to be planar?
No, they do not. As again, they just have to be on a topological surface. So right, so like again, like you can, yeah. So
theoretically, the simplest one is just like a filled dot and a non-filled dot connected by a line.
yeah, that is, yep. That you can have that.
Yo, what about complete graph on 7 vertices on a torus?
Complete graph of 7 vertices.
I mean, this is an example of a graph that isn't planar and can only be embedded on a torus, can't be embedded on a sphere. So that's why I mention it, but you don't have to draw it.
I think it would make sense, but you'd have to add some vertices to make it too colorable, right?
Yeah.
Oh yeah, okay. So anything that you can make bicolored. That is like can be a dessine. Oh, and also you have to make sure that no, I won't. All right, I won't say anything else. I'll just move on for now. All right, so now this might seem like a little out of the blue at first, but trust me, it'll be important because what we're gonna wind up using permutations to represent dessines. So first, let's talk about what a permutation is, because probably not everyone here has worked with permutations before. So a permutation is just a one-to-one map from a finite set to itself. And an example is, like, let's say your set is the numbers from 1 through 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you want to map this set of numbers to itself. And you can do this, for example. You can send 1 to 2, you can send 2 to 7, you can send 3 to 1, and then blah, blah, blah. You see it in front of you. I don't have to read it all out. But as you can see, like, every number that appears up here appears down here exactly once, right? So that's because it has to be a one-to-one map to itself. All right, so one convenient, but this is kind of a whole lot of stuff to write out. So a convenient notation we use is cycle notation for permutations. So and any permutation can be expressed this way. And I'll give an example like for this permutation up here. But again, like you can do a similar thing for any permutation. So you start with like a left parenthesis, and it doesn't matter which number you start with, but I'm going to start with 1 because that's the smallest number here. And so what you do is you look at the permutation and see, well, where does 1 go? So in this permutation, 1 goes to 2. So in the cycle, you write a 2 next to 1. And now you look at where 2 goes. So 2 goes to 7. So you write a 7 after 2. And then you look at where 7 goes. 7 goes to 4. So you write a 4 next to 7. Now you look at where 4 goes. 4 goes to 3. So you write a 3 next to 4. And then you look at where 3 goes, and 3 goes to 1, which is at the beginning of the cycle. And since your cycle has like gone back to the beginning, you close it up with a final parenthesis. And now we still haven't used all the numbers here, So we have to go on. So like, what's like the smallest number of users? So we haven't used 5 yet. So we do the same thing now. So 5 goes to 8, 8 goes to 6, and 6 goes to 5, so then you close it. And now finally we still have 9 and 10, so we'll start with 9, 9 goes to 10, and 10 goes to 9, so we can close it. Okay, so what this means is that like these like basically go around in a circle. So like if you were to apply this so this permutation is like, if you were to apply this to like any number, you would kind of like say like, you would basically just follow it along through like these cycles, right? So and when the number's at the end of a cycle, it just means that, okay, that means that 3 gets sent to the number that's at the beginning of the cycle. All right, does that make sense? Is everyone following along? Anyone not following along? Okay. Okay, so then I'll move on then. So now what we can do is we can compose 2 permutations together by, we kind of like do like, it's like a sort of multiplication in a sense. So what you can do is you can write like the 2, once you've written your permutation as a cycle, you can write the 2 cycles next to each other and then like kind of follow each number along to make a new cycle. So I'll give an example of that. So let's take these 2 permutations for now. So sigma is that one you see there, tau is this other one, and so now let's find the composition sigma tau. So you just write them next to each other. So sigma is 1, 3, 7, 2, 4, 5, 6, and tau is 1, 2, 3, 4, 5, 7, 6. And now what we want to do is we take like each number and follow it along to see what the new permutation is. So you start from the right when you're following through. So let's start with 1 here. So what does this do to 1? What does sigma tau do to 1? So as you start at the right, 5, 7, 6 doesn't do anything to 1. But now you get here and this cycle will send 1 to 2, okay? So now you have a 2. Then you go back, then you like move forward with a 2 in mind. 5, 6 doesn't do anything, now 2, 4. So now the 2 that you had gets sent to 4. And you follow that through and nothing else changes 4, so the end result is that 1 goes to 4. Okay? Now you do the same thing for 4. So you start at the right, first thing that happens is 4 goes to 1. And then as you go through, now you get to, the 1 goes to 3. So hold on a second. I lost my place in my notes. Okay, so now 4 goes to 3 in the new permutation. And now we see what happens to 3. So start at the right, 3 goes to 4, and follow through, 4 goes to 2. And so 1, 4, 3, 2. Now we see what happens in 2. 2 goes to 3, follow it along, 3 goes to 7. Now we start with 7, 7 goes to 6, 6 goes to 5. All right. And now 5 goes to 7, 7 goes to 1. And since we've reached the beginning, we close it now. And so what's left? We have 1, 2, 3, 4, 5. So the only number we haven't touched is 6. So let's see what happens to 6. So first 6 goes to 5, and then 5 goes to 6. So at the end of the day, 6 just goes back to 6. So that's kind of when a number just goes back to itself, we call that like the trivial cycle. So since 6 isn't moving, we don't really need to write it in the final cycle notation of sigma tau. So sigma tau is just 1, 4, 3, 2, 7, 5. Okay, and now and we can do the same thing for tau sigma. We are starting to run a little short on time, so maybe I won't do this example, just because it's the clock is ticking. I don't want to take more than an hour for the talk. All right, so another important idea is that every permutation has an inverse permutation, and that two permutations are inverses of each other if their composition is the identity. So we'll do as an example, sigma inverse, and kind of the way you find, basically the inverse has to do backwards everything that sigma does. So it's actually like pretty easy to come up with it, because you just need to do the whole thing backwards. So instead of sending 1 to 7, you have to send 7 to 1. Instead of sending 1 to 3, hold on. Okay, I got it backwards when I was doing this. So instead of sending 7 to 1, you want to send, it's basically like just all these cycles but backwards. Is like an easy way to conceptualize it. And to kind of check your work, you can try to multiply them. So sigma inverse times sigma is 7, 3, 1, 4, 2, 6, 5. And if you get back like if everything stays where it is when we follow through, we know that this is indeed the inverse. All right, and this is going to be equal to, so let's just see. So if we start at the right, 1 goes to 3, and then 3 goes to 1, so 1 stays where it is. Now if we start with 2, 2 goes to 4, and then 4 goes to 2, so again 2 stays where it is. And it's going to wind up being like that for all the rest of these numbers as well. So like everything's just going to stay exactly where it is. So what's that? Or did you say something? Composition is not commutative. Okay, right. Okay, yeah. So someone in the chat asked if composition is commutative, and the answer is in general no, for inverse permutations. Like if two permutations are the inverse of each other, then they commute. And sometimes they also, yeah, so if they're disjoint, they also commute. So if like none of the same numbers appear in either of them, then they'll commute. So like, for example, the cycle, you can change the order of the cycles in sigma and it'll still be equal to sigma. But in general, not all permutations commute. And we probably would have seen that if I wrote out what tau sigma is. But again, I don't want to take a whole lot of time to do that. So yeah, and we can also like, for the identity permutation, we can just write that as 1, because the rest of them don't matter because they're all just staying in place. And again, we could also do the same thing for tau inverse, but again, I kind of want to move on because I don't want to take up too much time with just this. Does anyone have any questions on permutations? Okay. So now, permutation representations of dessins. This is kind of like the main, like, cool thing I want to talk about. And you'll see, like, in a minute why this permutation representation is so important. So first, what you do is you take your dessine and you label all the edges with numbers, right? So 1, 2, 3, 4. Well, I'll draw an example in a second. So first you label the edges, then you take like kind of like a little circle around each vertex, and you write out a cycle by kind of listing the numbers of the edges in like the counterclockwise direction. Then what you want to do is like you take all the cycles from the white vertices and put those into one permutation that we will call sigma 0. Then you take all the cycles around the black vertices and put those all together into a permutation called sigma 1. And then the permutation of representation of the dessine is defined to be this pair sigma 0, sigma 1. So as an example, I'm actually going to use the picture that I had before, this picture. I think this is a good example to look at. So so first what we want to do, let's look first at the sphere. Okay, so we'll look at this one first. So let's label the edges. So and also all right, so here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I did not miss any edges, did I? Does that look like what it is? I think I'm good. Okay, so
Julian, the color is too
now,
light to see.
Yeah, okay, I'll change the color. I'll make that red. Can you see that better, or is that still not great?
I think it would be better if you don't write it on top of the edge, just write it in the white space.
Okay, I'm not going to rewrite it though. I think it'll take a while to rewrite it also. Oh, come on. Okay, so now let's come up with our permutation representation. So first, let's see what sigma 0 is. So this is the one that worries about the white vertices. So our white vertices are all these. Right, so with this one over here, right? Your first it doesn't really matter whether you do like a clockwise or counterclockwise direction, since there's only 2 of them. But like let's start with 1. We'll start with 1, and then like, if you kind of imagine turning counterclockwise around this little circle, the next edge you hit is 2. Then you keep going counterclockwise and you don't hit any more edges, so that means the first cycle's over. So that's the first cycle of sigma 0. And now for the next vertex, I don't want to. Okay, so for the next vertex, okay, whatever. All right. Next vertex, let's do maybe this one down here. So actually, let's do this one. So, right, so again, we can start with 3. It doesn't really matter which one we start with, but start with 3, and then we turn counterclockwise, we hit 4, and keep going counterclockwise, don't hit anything else when we get back to 3, so close parentheses. Same thing up here. We can do the same process. We'll get 5, 6 for our next, and then we'll get 7, 8 for this one. We'll get 9, 10, and 11, 12 will be the final one. Okay, so that's all of sigma 0 now. Then for sigma 1, sigma 1 is, so now we'll start with the black vertex. Let's start with the one that's at the top. So this black vertex, if we start with side 1, now you do have to be careful like what direction you're going in, because that affects what the permutation representation is. So we have to like imagine like we're viewing this from above. So if we're on one, and if we're viewing this from above, then we go like this. So right, so counterclockwise would be going this way. So the next one you hit is 6. And then if you keep going counterclockwise, you get to this one back here, which is 7. And then you get back to 1. Over here, if you start with 2 and go counterclockwise, you get 10, and then 3. Over here, if you start with 4, you go counterclockwise, you get 12, and then 5. And then the last one back here, this is the one where you have to be careful, because although counterclockwise, like for us would be, you know, this way, this is like, we have to imagine that we're viewing, we have to like imagine that we're on the other side of the sphere now. So like, so you would actually, okay, so people are asking questions that I haven't seen. Okay, yeah, I think that's a good point, that like, because we wanted to have like a direction for these permutations, that would make sense for why we need orientability. But yeah, you have to imagine that like the counterclockwise here isn't going to be actual counterclockwise, because we have to turn the sphere around in our faces. So this permutation is actually going to be like 8. And so like it'll be clockwise here, but it would be counterclockwise if we were standing on the other side of the sphere. So this would be 8, 11, 9. Okay, and I'm just going to specify that this is for the sphere. And this isn't, I mean, this isn't every dessine. Oh, actually, I don't know. I'm going to call this D1 and this one D2. So this is for D1. And we could do the same thing for D2. I don't know if does maybe someone want to like, maybe we could do that later if we have time. I think I'm running a little short on time. But we could also find a permutation representation for D2 if we like kind of label it in the same way. So, all right. And now the big very useful proposition is that if you let XD be any dessine and you let G be the genus, and G is like the genus of the dessine, then the genus actually is connected to this cycle decomposition, or cycle permutation representation, sorry. Right, so 2 minus 2G, so that's 2 minus twice the genus, is equal to the number of cycles in sigma 0 plus the number of cycles in sigma 1 minus the number of edges plus the number of cycles of sigma 1, sigma 0. And I'm not going to write out the proof, but you can like kind of verify it to yourself if you want, using something called the Euler Characteristic. yeah, so if you know what that is, like, you can probably kind of see what the Euler characteristic basically says that 2 minus 2g is equal to like the number of vertices minus the number of edges plus the number of faces of a surface. And it turns out that the number of cycles in sigma 1, sigma 0 winds up being equal to the number of faces in the dessine. The number of vertices is obviously the number of cycles of sigma 0 plus the number of cycles of sigma 1, because there's exactly one cycle in sigma 0 for each white vertex, and there's exactly one cycle in sigma 1 for each black vertex. Right, so that's kind of how the proof works out. And if we want to do our example from before, let's go back to our permutation representation for D1 for that dessine we had on the sphere. All right, so we should, well, first I'll quickly compute sigma 1, sigma 0. Okay, so let me just work this out. So well, do you want to like do this together maybe so we can have a little more audience interaction? So sigma 1, sigma 0 basically means like you go through sigma 0 first and then sigma 1. So like, where's 10 going to wind up when we do this?
Eight.
Right, so yeah. All right, and now where's 8 going? Right, so where does 8 go in sigma 0? 8 goes to 7, and then in sigma 1, 7 goes back to 1, so that's the end of this. So now 2 is going to 1, and then 1 goes to 6, so 2 goes to 6. 6 goes to 5, 5 goes to 4, 4 goes to 3, 3 goes to 2. That's the end of that. Let's see, now 3 goes to 4, 4 goes to 12. 12 goes to 11, 11 goes to 9, 9 goes to 10, and 10 goes to 3, so that closes up, and we just have one more, I think. All right, 5 goes to 6, 6 goes to 7, 7 goes to 8, 8 goes to 11, and now 11 goes to 12, and in here 12 goes back to 5. So there we go. So that's sigma 1, sigma 0. So now if we try, so we should get, so 2 minus 2g we should wind up getting that g equals 0 if we follow through this, right? So the number of cycles in sigma 0 is, just count these. So 1, 2, 3, 4, 5, 6. 6 plus the number of cycles in sigma 1, which is 1, 2, 3, 4, minus the number of edges, and the number of edges is just 12, because that's, you know, that's all that we added up, plus the number of cycles in sigma 1, sigma 0, so that's 1, 2, 3, 4 cycles in sigma 1, sigma 0, that's plus 4. And now that gives us 2 minus 2g equals, that's minus 2, right? Something, or am I wrong? Nope, that's positive 2. Okay, yeah. And so then we get minus 2g, right? If we subtract 2 from both sides, both loop, minus 2g equals 0, which means g equals 0. So yay, our permutation representation gave us the correct genus. And if we were to find the permutation representation for D2, we would wind up getting, and we put it back into this equation, we would wind up getting that the genus is 1. So somehow the way the edges are kind of positioned relative to each other matters, because it changes what the permutation representation is, which changes what genus you're going to get when you put it into this equation. So that's kind of why, like, you can't just consider abstract graphs floating in space, because when it's an abstract graph floating in space, it doesn't really matter where each edge is relative to the other edges. But for dessins, it does matter, because it affects what genus you're on. All right, and we can actually, I won't get into this too much, but so long as, like, if you have any two permutations, like, so long as they fit like certain conditions, you will be able to get, that means that you will be able to get a dessine back from them. So the condition is that it has to be a transitive, that they have to generate a transitive group, which is like, again, like, I don't want to define all of abstract algebra right now. So we're not going to talk to you a whole lot about that. So any questions before I go forward? So is this something that, the question is this something that any graph tells you about the surface, or is there something specific graphs tell you about the surface? Well, any like bicolored graph you have on a surface is going to give you the same, it's going to work in the same equation no matter what, right? Like, and like any dessine that you have on a sphere is you're still gonna be able to find a permutation representation, plug it into this formula, and get get 0 for G. I'm not sure if that's what you're asking. Okay, I'm going to just kind of, I'm almost at the end here. There's just like a couple more, there's one more thing I want to point out, and then I'll just wrap up. So like one interesting fact is that, like, if we label the edges differently, you can get back the same permutation representation just by conjugating, which at the end of the day basically means that even if you relabel the edges, the permutation representation is essentially the same. So just what conjugating means is, like, if sigma 0, sigma 1 is your original permutation representation, and then you relabel the edges, and your new permutation representation is like sigma 0 star and sigma 1 star. Yeah, what Ajmain said is that the permutation representation depends on which surface your graph is located on, because you have to look locally at the surface to determine which edges form a cycle around it. Yeah, so it's because you're like looking at it on this close-up level where, like, yeah. So now again, just like back to conjugation. So like if these are like the same different permutation representations for the same dessine because we've relabeled the edges, then that means there exists another permutation, we'll call it tau, such that if you compose these permutations together with tau and tau inverse, you get the new representation. So if you take if you have tau sigma 0 tau inverse, you get sigma 0 star. And if you take tau sigma 1 tau inverse, you get sigma 1 star. And I guess like its interesting feature is that it's the same tau that like, so that brings you to both of these. So like these are the same tau. Like tau is not different between these two. Like it's one permutation that works for both of these. And what conjugation means is that you multiply on one side with a permutation and on the other side with the inverse. So that's just what conjugation means. And very important note is that equivalent dessins have the same permutation representation up to conjugation. So earlier on, when I said, you know, like, right, that two dessins are equivalent if there's like an orientation preserving homeomorphism that induces an isomorphism between the graphs, which again, like intuitively is just like a nice map that makes things look equivalent to each other. So if when dessins are equivalent, their permutation representations are essentially the same thing. Okay. Anyone have any questions? And also that conjugate, and also works the other direction too, where if you take any like conjugate permutation representations, they will give you equivalent dessins. All right, so no one's saying anything, so this is just kind of my closing statement here. We're done with most of the math for tonight. So yes, kind of my closing statement is that like this is just like an introduction to an introduction. There's a lot more math going on with dessins than I have time to talk about tonight. I actually learned about this last year in like the MAT. What number is it? My mind's blanking on the number of the course. But it's the MAT seminar course that I took last year. Yeah, 401. Okay. Yeah, so I learned it with Professor Berger, who's actually in the Zoom call tonight. And we, you know, like we studied this for like a whole semester, and we didn't even get through the whole book. So like there's a lot of stuff going on with these. And the book that I kind of learned from, and that I got the picture from, and that I like referred to for a lot of things regarding this is this book called Introduction to Compact Riemann Surfaces. This is what it looks like. It's blue. So yeah, and as you can see, like, so yeah, that's why I'm saying this is an introduction to introduction, because the book is called Introduction, and my talk is basically just an introduction to that. And before I kind of glossed, you know, we didn't really talk about Riemann surfaces in particular, but like basically the Riemann surface means that you're putting like a complex structure on topological surfaces. And this starts to become really important when you start talking about these special functions called Bailey functions, and that wind up having like a really nice correspondence to dessins. Yeah, but again, like that involves a lot of things I would have to define, and it would take forever to talk about. So I don't have time to do that tonight. Yeah, so that's all I have for you. As any lingering questions? All right, Ajmain's clapping, so I'll say the end.